As I mentioned at the end of the last short video, there is another form of active second order filter which allows you to set the resonant frequency, the gain and the Q factor independently. It's particularly useful therefore in cases where you want the passband, that's the low frequencies, to have a gain of 1. This is the circuit. It's a little bit more complicated to analyse than the previous circuit, but if you do decide to plump through all of the algebra, then this is the form of the frequency response that you will get. You'll notice that unlike the last second order active filter we looked at, this one is based on an inverting op-amp. So at low frequencies, the output is 180 degrees out of phase with the input. There's nothing magical, there's no tricks in the derivation of this frequency response. All you have to do is apply the same type of nodal analysis techniques that we've done before, labelling this point in the circuit X again. The current flowing into X would be Vin minus X over R1. The current flowing out of X, well, that would be some current flowing down through C1, which would be X over 1 over j omega c, plus the current flowing through R2, which would be X minus V out over R2, plus the current flowing through here. And the current flowing through here would all have to flow through C2 as well, since, assuming this is an ideal op-amp, no current flows in to the inputs of the ideal op-amp. So the current flowing through R3 would just be X minus V out over R3 plus 1 over j omega C2. Then we can note that for this op-amp to be in its linear region, its two inputs must be at approximately the same voltage, and the non-inverting input is tied to ground, so the inverting input must be at effectively a 0 volt or ground voltage as well. And therefore, we'd have that the current flowing through R3, that would be X over R3, it's really X minus 0 over R3 because we know the voltage here is 0, must be the current flowing through C2, and the current flowing through C2 would be 0 minus V out, I'll just write that as minus V out, over 1 over j omega C2. And again, we've got two simultaneous equations, and we need to eliminate the variable x between these two simultaneous equations, and then rearrange all the terms that we have left, so we have something of the form V out over V in, and that is our frequency response. And again, the algebra is fairly tedious to do, details in the short introductions if you want. This is the answer that you should come out with. And comparing this to the standard form of a second order response, the gain at DC over 1 plus j omega over q times resonant frequency plus j omega squared over the square of the resonant frequency, we can see that the resonant frequency, omega naught squared, must be 1 over C1, C2, R2, R3, and therefore resonant frequency is 1 over the square root of that lot. And Q times the resonant frequency is 1 over the coefficient of j omega, which in this case is C2 R2 plus R2 R3 over 1 C2 plus R3 C2. And therefore Q is square root of C1, C2, R2, R3 over, and there's a common term in C2 I can extract from the denominator, leaving me with this. So, to summarise, the gain at low frequencies, minus R2 over R1. The Q factor is given by this expression, and the resonant frequency by this expression. And this does allow you to set the Q factor and the resonant frequency and the gain at low frequencies independently. If you want to have a gain of 0 dBs, or -1 in this case, since it's an inverting amplifier, at low frequencies, then you just need to set R1 and R2 to have the same value. Now, while it is possible to set these three parameters independently, it's perhaps not immediately obvious how to do that. One technique is perhaps to pick values of R1, R3, C1 and C2 to give you the resonant frequency that you want, and then pick R2 to give you the value of the gain that you want, since the resonant frequency is not a function of R2, and then to get the Q factor to change the ratio of C1 and C2 while leaving their product the same. To design a practical filter, though, we've also got to take account of the fact that capacitors only tend to come in E6 series values. So we end up simulating this in any case to make sure that the circuit that we can build with available components has an acceptable performance in our application. This is a real example of such a filter taken from a Texas Instruments application sheet. It's designed for an audio system to get rid of any frequencies above the human hearing range while giving as flat a gain as you can to all of the frequencies within the human range. And they've done that by picking a resonant frequency of around 30.2 kHz and a Q factor of 0.8, which is about as close as you can get to 1 over root 2 with practical component values. This is a simulation of the circuit, and you can see that with the Q factor of 0.8 we do get a small amount of resonant peaking at around about the resonant frequency. The output is just over 1 here, but over most of the human hearing range, from very low frequencies up to around 20 kHz or so, the output is very close to 1, in other words 0 dB gain. And then it plummets down at 40 dBs per decade, as we would expect a second order low pass filter would. There are a lot of other different topologies of active filters as well. I won't go through any more of them here. You may come across them. You can analyze them all just by the same type of technique as we've done here. Apply nodal analysis with phasors and complex impedance and work out the frequency response. Then by comparing to the standard form, you can work out the Q factor and the resonant frequency. What I want to look at next is adjustable filters, tone controls.